Our entire cosmic history was forged in less than a single heartbeat. In the first second of existence, the universe underwent transformations more dramatic than any in the billions of years that followed. This is the story of when the universe was younger than a second, a journey to the very edge of what we can know. By the end, you will understand how this fleeting moment decided the fate of every galaxy, star, and atom in existence. We will confront a realm where time itself had no meaning and explore how a ghostly sea of particles set the stage for everything. How does it feel to know your own origin story is written in that impossible first instant? At time zero, the universe was not a place but a potential. Our story begins in the Planck epoch, a span of existence so brief it defies human comprehension, from the very first instant to about 10 to the negative 43 seconds. In this primordial state, the very fabric of reality was woven from conditions we cannot replicate and barely understand. All four fundamental forces that govern our cosmos today, gravity and electromagnetism, along with the strong and weak nuclear forces, were fused into one single, perfect superforce. This was a unity so complete it represents the ultimate frontier of physics, a realm where our current laws simply break down and cease to apply. The scale of this moment is defined by the work of Max Planck, whose constant gives this epoch its name. The temperature was an inconceivable 10 to the 32 Kelvin, a number so vast it describes pure energy. The entire observable universe was compressed into a volume smaller than a Planck length, a distance so minute it is the smallest meaningful measurement in physics. In this state, space and time as we know them did not yet exist in a stable form. They were quantum entities, fluctuating and foaming, meaning the concepts of before and after, here and there, lose all familiar meaning. This era is the ultimate blank slate, the first page of the cosmic story where the pen has yet to touch the paper. Modern cosmologists describe it as the greatest mystery, pushing our theories of relativity and quantum mechanics to their absolute limits, where they contradict each other and fail. How do we conceptualize a state where time itself is not yet defined? We cannot use clocks or rulers. We can only use mathematics and logic to peer into the abyss, understanding that everything to come, every galaxy and star, was encoded in the conditions of that first, unimaginable flash. This foundational mystery sets the stage for the first great transformation, the moment unity shattered and the forces of nature were born. From this state of pure potential, we are drawn to the most famous and frustrating question in all of science. What, if anything, came before the Big Bang itself? This is not merely a question of what happened earlier, but whether the idea of earlier even makes sense. To grasp the difficulty, think of asking what lies north of the North Pole. The question sounds logical, but the framework of our map provides no answer, because at that exact point, the very concept of north ceases to exist. The classical Big Bang theory describes a similar boundary, a gravitational singularity, a moment of infinite density and temperature where the known laws of physics simply stop working. Our equations, which so beautifully describe the expanding universe, hit a wall and dissolve into infinities, telling us nothing about what caused the bang or what preceded it. This is why leading minds have proposed ideas that stretch our understanding of reality itself. Stephen Hawking, for instance, suggested we think not in ordinary time, but in something called imaginary time, a mathematical dimension where the universe has no boundary, no beginning point, much like the surface of the Earth has no edge. In this view, asking what came before the Big Bang is like asking what is south of the South Pole, a question that loses its meaning on a closed surface. Other theories, like the cyclic model, propose a perpetual cosmic rhythm, where our universe is just one in an endless sequence of expansions and contractions, a great cosmic breath with no first inhalation. Each of these ideas is an attempt to move beyond the dead end of the singularity. Ultimately, the core of the problem is time. Our intuition tells us that every event must have a cause that came before it. But if time itself began at that singular moment, then the word before becomes meaningless. There was no time for a cause to exist in. This challenges the very foundation of how we think about existence. The singularity represents the limit of Albert Einstein's theory of general relativity, telling us clearly that a new theory, one that marries gravity with quantum mechanics, is needed to peer beyond that veil. So we are left with a profound enigma. If there truly was no before, then how did everything we see come to be? This question hangs in the air, compelling us to look at the very first fractions of a second after the singularity, where the first tangible structures of our reality began to crystallize from the formless fire. The singularity's veil lifts to reveal the first tangible event in cosmic history, a transformation so violent it redefined existence itself. This was cosmic inflation, a growth spurt more explosive than any supernova, where the universe expanded faster than the speed of light in a fleeting instant between 10 to the negative 36 and 10 to the negative 32 seconds. Imagine a single atom swelling to the size of our entire galaxy, and then far beyond, in less time than it takes light to cross a proton. This is not the steady expansion we see today, but a runaway stretching of the fabric of spacetime, driven by a force so potent it makes every subsequent event seem slow and gentle. The theory, pioneered by physicist Alan Guth, was born from a need to solve deep mysteries. Why does the distant universe look so remarkably uniform in every direction, as if it had been thoroughly mixed? And why is the geometry of space so perfectly flat, like a vast, endless sheet, rather than curved? Inflation provides an elegant answer. It proposes that the entire observable universe we see today was once a tiny, homogeneous patch, smaller than a marble. This patch was then stretched to cosmic proportions so rapidly that any initial irregularities were smoothed away, ironing the cosmos into the uniform flatness we observe. The engine behind this incredible expansion was a hypothetical field that permeated the infant universe, known as the inflaton field. Think of this field like a cosmic landscape, where the universe initially found itself perched high up on a steep slope, a state of immense potential energy. This unstable state could not last. As the universe cooled from its initial fire, the field underwent a phase transition, rolling down that slope like a ball settling into the bottom of a valley. As it rolled, it released its colossal stored energy, not as heat or light, but as raw, repulsive gravity that pushed every point in space away from every other point at an exponential rate. This energy did something even more profound. It took the faintest whispers of the quantum world, the tiny fluctuations that exist even in a vacuum, and stretched them to astronomical scales. These amplified ripples in density became the seeds for all future structure in the cosmos. Every galaxy cluster, every swirling spiral of stars, every planet, and every one of us originated from those microscopic quantum tremors inflated to cosmic proportions. Without this brief, hyper-accelerated sprint, the universe might have remained a formless, thin soup of particles, never clumping into the magnificent structures we see today. So what brought this frantic expansion to an end? The inflaton field eventually reached the bottom of its valley, its potential energy spent. This energy decayed, reheating the universe into a hot, dense plasma of particles, setting the stage for the next great act. The most dramatic transformation was over, leaving behind a smooth, stretched, and seeded cosmos, ready for the laws of physics as we know them to finally take command. With a frantic sprint of inflation over, the universe settled into a new and bizarre state of being. It became a seething, opaque broth, a primordial soup so dense and hot that light itself could not travel through it. For a fleeting span from about 1/1,000,000th to 1/1,000,000th of a second, all of existence was filled with what physicists call a Quark-Gluon Plasma. This was a state of matter unlike any you have ever seen, where the most fundamental building blocks of everything we know roamed completely free. Imagine a superheated, impossibly dense fog, a churning ocean of energy where the particles that would one day form every proton and neutron in your body were unable to bind together. They simply swam in a collective, chaotic sea. This plasma was the domain of the strong nuclear force, the mightiest of the four fundamental forces, which normally acts like an unbreakable glue, holding quarks together inside protons and neutrons. But in the extreme heat of the early universe, that glue was melted. Quarks and the particles that carry the strong force called gluons existed in a liberated, soupy state. We know about this not just from theory, but from incredible experiments that turn back the cosmic clock. Inside massive particle accelerators like the Large Hadron Collider, scientists smash heavy atomic nuclei together at nearly the speed of light. For a split second, in the heart of those collisions, they recreate a tiny speck of this primordial quark-gluon plasma, allowing us to study its properties directly. It behaves not like a gas or a liquid, but as a nearly perfect fluid with almost zero viscosity, flowing with a surprising lack of internal friction. This could not last. The universe was still expanding, and expansion means cooling. As the temperature plummeted below a critical threshold, roughly 2 trillion degrees Kelvin, the strong force finally regained its grip. In a universal process known as hadronization, the free-roaming quarks and gluons suddenly condensed, snapping together into stable composite particles called hadrons, the family that includes protons and neutrons. It was a cosmic change of state, akin to water vapor in a steamy room suddenly condensing into droplets on a cold window. In that moment, the chaotic primordial energy began to crystallize into the first stable matter. The fog was clearing, and the first permanent structures of our reality were emerging from the haze. This quark-gluon plasma was the essential cradle, the forge where the raw ingredients for every atomic nucleus in the cosmos were first prepared. What would it have been like to witness a universe transitioning from a formless sea of energy into something that could finally be called stuff? That transition set in motion a chain of events where matter would soon face its greatest and most mysterious rival. But from that first condensation of matter, our universe faced an immediate and existential threat. The Big Bang, in its perfect symmetry, should have created precisely equal amounts of matter and its mirror opposite, antimatter. For every quark forged, an antiquark should have been its twin, and when matter meets antimatter, they do not simply coexist, they annihilate each other in a flash of pure energy, leaving nothing behind. If the recipe had been perfectly balanced, every particle would have found its counterpart. The entire universe would have vanished in a brilliant, silent flash, leaving behind an eternal, empty sea of light. Yet here we are, made of matter, in a cosmos filled with galaxies, stars, and planets. Our very existence is proof that something went wonderfully, mysteriously wrong with that perfect symmetry in the first second. This is the profound puzzle of baryogenesis, the birth of an imbalance that allowed the material world to be. To create a universe that survives its own birth, three very specific conditions had to be met, principles laid out by physicist Andrei Sakharov. First, the total number of baryons, which are particles like protons and neutrons, must be capable of changing. This is called baryon number violation. Think of it as needing a rule that can be broken, a cosmic ledger where the columns for matter and antimatter are not permanently locked. Second, the processes governing particles must treat matter and antimatter slightly differently. This involves the violation of both charge symmetry, which flips positive to negative, and charge parity symmetry, which also mirrors left and right. If the laws are perfectly symmetrical, matter and antimatter behave identically, and no imbalance can ever arise. We have actually observed this subtle favoritism in laboratories. In studies of certain rare particle decays, like those of kaons and b-mesons, scientists have watched matter and antimatter versions decay at slightly different rates. It is a tiny, fractional difference, but it is real, proving the laws of physics have a slight bias. Third, all of this must happen out of thermal equilibrium. The universe cannot be a perfectly mixed, uniform soup during this process. It needs some kind of shift, a phase transition or a sudden change, to lock in the asymmetry before everything remixes and cancels it out. These three conditions converged in the hot, evolving chaos of the early universe. Through mechanisms we are still working to understand, perhaps involving grand unified theories or interactions with exotic fields, they produced a staggering result. For every 1 billion antiquarks, there were 1,000,000,001 quarks, a 1 part in a billion excess of matter. It seems insignificant, but when the Great Annihilation finished, that one extra particle in every billion was all that remained. Every single atom in your body, every star in every galaxy, is made from the ashes of that near-total mutual destruction, the survivors of the most catastrophic war in history. That minuscule surplus is the entire material universe, so the question becomes not why is there something rather than nothing, but why is there so much more of this particular something? The answer lies in a flaw in perfection, a crack in cosmic symmetry so precise it feels almost designed. How did the raw, energetic chaos of the first moments settle on such a specific, life-allowing number? This fine-tuned outcome points us toward the next great act, where those surviving particles would finally begin to build something stable from the wreckage. That 1 in a billion surplus of matter was now poised to build, but first, the universe had to decide what kind of building blocks it would use. Before even a trillionth of a second had elapsed, the cosmos was still a place of profound unity. 2 of the 4 fundamental forces we know today, electromagnetism and the weak nuclear force, were not separate entities. They were fused into a single, elegant electroweak force. In this high-energy arena, the particles that carry these forces were indistinguishable. The photon, which we know as the particle of light and electromagnetism, and the massive W and Z bosons, which mediate the weak nuclear force responsible for processes like radioactive decay, were all the same type of particle. They moved through a universe that was still too hot and energetic for their differences to matter. It was a state of perfect symmetry, a blank canvas where the rules were beautifully simple, but where nothing had any substance. For a universe to become complex, that symmetry had to shatter, and it did in a transformative moment around 1 picosecond, or 10 to the negative 12 seconds after the beginning. As the cosmos expanded and cooled below a critical temperature of about 10 to the 15 Kelvin, something remarkable happened in the invisible fields that fill all of space. The Higgs field, which had existed in a symmetric, high-energy state, underwent a dramatic phase transition. Think of it like a vast ocean of superheated water vapor. As it cools, it must suddenly condense into liquid and then freeze into ice. The transition is abrupt, and the final state, the ice, has properties the vapor did not, like solidity and shape. The Higgs field froze into a new, stable configuration. This event is the famous Higgs mechanism. As the field settled, it began to interact with other particles moving through it. Some particles, like the W and Z bosons, interacted with this cosmic treacle very strongly, slowing them down and giving them mass. Others, like the photon, slipped through completely unaffected, remaining massless. This single act of cosmic differentiation broke the electroweak symmetry. The once unified force split into the two distinct forces we recognize today, electromagnetism and the weak force. The confirmation of this mechanism was one of the greatest triumphs of modern physics, culminating in the discovery of the Higgs boson at the Large Hadron Collider at CERN in 2012. By recreating energies not seen since that first picosecond, scientists proved that this field exists and behaves exactly as predicted. The consequences of this breaking are woven into the fabric of our reality. If the Higgs field had given different masses to the fundamental particles, or if the symmetry had broken in another way, the universe would be unrecognizable. The electron's mass is precisely tuned to allow for stable atoms and the complex chemistry that builds molecules. If it were even slightly different, atoms could not form and stars could not burn. The distinct nature of the weak force allows for the nuclear reactions that power stars and create the heavier elements. This moment, this freezing of a field, defined the very rulebook of physics. It decided which particles would be heavy, which would be light, and which would race forever at the speed of light. It set the stage for everything that follows, from the first atomic nuclei to the chemistry of life itself. What if the symmetry had broken differently? We would not be here to ask the question. The universe would be a dark, simple, and utterly alien place. With the forces now distinct and particles endowed with mass, the stage was finally set for the survivors of the Great Annihilation to come together and form the first enduring structures of the cosmos. The universe, now stocked with protons and neutrons from the quark soup, was about to become a much more dynamic place. We enter the Lepton epoch, a time spanning from about 1,000th of a second to a full second after the beginning, where the cosmos was ruled by the lightweights. The dominant players were no longer the heavy hadrons, but a family of particles called leptons, most notably electrons and their antimatter twins, positrons. Billions upon billions of these charged particles filled every cubic inch, buzzing through a dense fog of pure energy. This was still a universe far too hot and violent for atoms to exist. Electrons and positrons, being matter and antimatter, were constantly being created from collisions of pure energy, living for a fleeting moment, and then finding a partner to annihilate within a flash of light. It was a frenetic, brilliant dance of creation and destruction, a cosmic firestorm where light was constantly being born, and that light, in the form of photons, was utterly trapped. With so many free charged particles zooming around, a photon could not travel any meaningful distance. It would immediately smack into an electron or positron and be scattered in a new direction. This made the entire universe completely opaque, a glowing, impenetrable plasma like the heart of the densest star. Yet within this brilliant chaos, a profound and silent exodus was taking place. Among the leptons are the ghostly neutrinos, particles so insubstantial they barely interact with anything at all. As the universe expanded and its density dropped, there came a point, around 1 second after the beginning, when the distance between particles became just large enough that neutrinos simply stopped colliding. They decoupled from the cosmic plasma. In an instant, trillions of them began streaming freely through space, never to interact significantly with matter again. This created a cosmic neutrino background, a whisper from the first second that should, in theory, still be washing through the universe today, a fossil even more ancient than the cosmic microwave background. Detecting it directly remains one of the great challenges of modern cosmology, a ghostly signal from the universe's fiery infancy. Meanwhile, the great electron-positron dance was reaching its finale. As the temperature continued to plummet, the energy of the photon sea was no longer sufficient to spontaneously create new pairs. The existing pairs met and annihilated in one last great wave. But remember the critical asymmetry from earlier, that 1 in a billion surplus of matter. For every billion positrons, there was one extra electron with no partner to annihilate with. When the brilliant flash of mutual destruction faded, those leftover electrons were all that remained of the Lepton hordes, and what of the immense energy released from all those annihilations? It did not vanish, it poured into the sea of photons, supercharging the cosmic radiation field. In that moment, the balance of power in the universe shifted fundamentally. The era of particle dominance was ending. The universe, now cleared of most free charged particles, was poised for a sudden, breathtaking transformation. For the first time, light was about to break free. The brilliant flash of annihilation faded, and a new kind of quiet descended upon the cosmos. The universe, now just a few seconds old, had cooled to a temperature where something monumental could finally happen. The surviving protons and neutrons, the heavy survivors of the quark sea, were no longer simply bouncing off each other in a frenzied plasma. They were now slow enough and the density just right for the strong nuclear force to reach out and lock them together. This marks the beginning of primordial nucleosynthesis, the universe's very first and only starless nuclear furnace. For a brief window between 1 second and about 3 minutes after the beginning, the entire cosmos became a reactor, forging the first atomic nuclei from the primordial fire. The main fuel was the simple proton, the nucleus of a hydrogen atom. The first step was the most delicate. A proton and a neutron had to collide and stick, forming a nucleus called deuterium or heavy hydrogen. In today's universe, this is a routine step inside stars, but in that first minute, it was a race against time. The sea of photons was still so intense that these fragile deuterium bonds were constantly being blasted apart by high-energy light, a process called photodisintegration. It was only when the universe cooled below 1 billion degrees that deuterium could finally survive. Once that bottleneck was passed, the nuclear chain reaction exploded. Deuterium nuclei rapidly collided with more protons and neutrons, building up the next element, helium-4. This 2-proton, 2-neutron nucleus is incredibly stable, a perfect little nuclear package. In those 3 minutes, nearly all the available neutrons were swept up into helium-4. When the furnace finally shut down, as expansion diluted the particles too far for further fusion, the cosmic chemistry was set. By mass, the universe was about 75% hydrogen, 25% helium, and only the merest traces of deuterium, helium-3, and lithium-7. This prediction is not just a theory, it is one of the strongest pillars of evidence for the Big Bang. When astronomers measure the oldest, most pristine clouds of gas in the universe, they find this exact ratio. The abundance of that fragile deuterium is especially critical. It acts as a cosmic barometer for the density of ordinary matter in the early universe. Too dense and all the deuterium would have been cooked into helium. Too sparse and more would have survived. The fact that the observed amount matches the prediction with stunning precision tells us our understanding of that first 3 minutes is profoundly correct. This outcome was balanced on a knife's edge. The expansion rate of the universe during those minutes was the master dial. If the universe had expanded just a fraction faster, particles would have been pulled apart too quickly, and even less helium would have formed. If it had expanded slightly slower, the nuclear reactions would have continued longer, fusing almost all the hydrogen into helium. A universe of mostly helium would be a cosmic desert, as helium stars burn in vastly different ways. The first stars might never have ignited, or their life cycles would have been utterly alien, potentially leaving no carbon, oxygen, or other elements essential for planets and life. This fine-tuned 3-minute period gifted the cosmos with its foundational chemistry, a simple but perfect fuel mixture. For the next several hundred million years, the universe would be a dark, expanding cloud of this hydrogen and helium gas waiting. The stage was set, but the actors, the brilliant lights that would transform this simple gas into the periodic table, had yet to appear. How does a dark, uniform cloud of two elements ignite into a billion points of light? For nearly 400,000 years, the universe remained a glowing, opaque fog. Then, in a cosmic transition more profound than any sunrise, everything changed. As the expanding cosmos cooled below a critical threshold of about 3000 Kelvin, a fundamental shift occurred. The free-roaming electrons that had been scattering light for eons finally slowed down enough to be captured by atomic nuclei. Protons snatched up electrons to become stable hydrogen atoms, and helium nuclei did the same. This process, known as recombination, was not a sudden explosion but a gradual settling, like a stormy sea finally growing calm. The last scattered flashes of light from electron collisions faded, and a great silence fell. But this silence was not darkness. It was the moment the universe became transparent. For the first time, photons, particles of light, could travel in straight lines without constantly bumping into charged particles. The cosmic fog had lifted, and the light that had been trapped since the first second was suddenly set free. This monumental release of radiation is what we call the cosmic microwave background, and it is the oldest picture we have of the entire cosmos. Think of it as the universe's very first baby photograph, taken when it was only a fraction of its current age. This image is not a photograph in the conventional sense, of course. It is a map of tiny temperature differences imprinted on microwave radiation that has been traveling for over 13 billion years, now cooled to just a few degrees above absolute zero. What is truly staggering about this picture is its near-perfect uniformity. No matter which direction we look, the temperature of this background radiation is almost exactly the same, varying by only about 1 part in 100,000. This incredible smoothness is the direct result of cosmic inflation, that hyper-accelerated sprint in the first fraction of a second. Inflation stretched a tiny, homogeneous patch to become our entire observable universe, ironing out any major wrinkles. Yet those minuscule fluctuations, those 1 part in 100,000 variations, are the most important part of the picture. They are the cosmic seeds. These faint ripples in temperature correspond to slight over-densities and under-densities in the early plasma, places where gravity had just a little bit more, or a little bit less, to work with. They are the imprints of the quantum fluctuations from the inflationary epoch, blown up to cosmic size. Every galaxy cluster, every void in the vast cosmic web, grew from these subtle imperfections. We have not just theorized about this background glow, we have captured it in exquisite detail. A series of pioneering space missions have turned this theoretical echo into a precise cosmic blueprint. The Cosmic Background Explorer, or COBE, first confirmed the perfect blackbody spectrum of the radiation and detected the anisotropies, the tiny temperature differences, in the 1990s. Its successors, the Wilkinson Microwave Anisotropy Probe, WMAP, and the European Space Agency's Planck satellite, mapped these fluctuations with breathtaking precision. The Planck map, a mottled oval of blues and reds resembling a celestial coffee stain, is arguably one of the most important scientific images ever created. By analyzing the patterns in this map, cosmologists have extracted a treasure trove of data. It tells us the universe is 13.8 billion years old. It confirms the critical density and flat geometry predicted by inflation. It quantifies the exact amounts of ordinary matter, dark matter, and dark energy that make up the cosmos. This relic radiation is our most direct observational link to the universe's infancy, a message in a bottle sent from a time long before the first stars flickered on. So what secrets do these ancient photons, which began their journey when atoms were first born, still hold about the first instance? They are a time capsule, but one with layers we are still learning to peel back. The patterns we see are a snapshot of the universe at 380,000 years old, but the processes that created those patterns, inflation, the separation of forces, the Quark-Gluon Plasma, all happened in the first second. By studying the statistical properties of the fluctuations, scientists can test theories about those earliest moments. Some search for faint imprints of primordial gravitational waves, ripples in spacetime from inflation itself, which would leave a distinctive curl pattern in the polarization of the CMB light. Others look for hints of exotic particles or extra dimensions that might have left a subtle signature. Each photon is a messenger from the dawn of time, and we are only beginning to understand its full vocabulary. This afterglow of creation surrounds us completely, a whisper from the beginning in every direction we look. It is the foundation upon which all of cosmic history is built. The cooled embers of the first fire, holding within its uniform glow the blueprint for everything that was to come. That uniform sea of ancient light holds a secret, a faint fingerprint of the chaos that birthed it. The majestic cosmic web of galaxies, with its vast clusters and immense voids, did not arise from perfection, but from the most fundamental kind of imperfection imaginable. Its origin lies in the quantum realm, in the first fleeting instance when the universe was smaller than an atom. According to Werner Heisenberg's uncertainty principle, empty space, even in its purest form, can never be perfectly still. It is a seething, bubbling foam where pairs of virtual particles and their antiparticles spontaneously flicker into existence for impossibly brief moments, borrowing energy from the vacuum before annihilating and vanishing again. In the calm of today's universe, this quantum jitter is usually invisible, a background hum of reality. But during the explosive sprint of cosmic inflation, something extraordinary happened. That hyper-accelerated stretching acted like a cosmic amplifier. Imagine a tiny, wrinkled balloon, its surface covered in microscopic bumps and dips. If you could inflate that balloon to the size of a galaxy, those tiny imperfections would be stretched into vast mountain ranges and deep canyons. Inflation did exactly this to the quantum fluctuations in the inflattened field. The microscopic jitters in that primordial energy field were frozen in place and stretched across the cosmos, transforming from fleeting quantum events into permanent, classical ripples in the density of matter and energy. These ripples became the seeds of all structure. Where the density was slightly higher, gravity had a stronger grip. Over hundreds of millions of years, that extra gravitational pull would slowly draw in more and more gas from the surrounding regions. These over-dense patches became the nurseries for the first stars and the cores of the first galaxies. The under-dense regions, conversely, evolved into the great cosmic voids we see today. This is why the pattern in the cosmic microwave background is so crucial. Those tiny temperature variations, mapped in exquisite detail by satellites, are the direct imprint of those amplified quantum seeds. They are the blueprints from which the entire observable universe was constructed. Every galaxy cluster, every swirling spiral of stars, every planet orbiting a distant sun traces its lineage back to a random quantum tremor in the first fraction of a second. Without that inherent randomness, the universe would have remained a perfectly smooth, featureless, and ultimately boring void. There would be no clumps of matter, no stars to forge heavier elements, no planets to form, and no one to ponder the cosmos. This reveals a profound and beautiful connection. The same quantum rules that govern the behavior of subatomic particles here on Earth also dictated the large-scale architecture of the entire cosmos. The random dice roll at the smallest scale determined where galaxies would blossom and where vast emptiness would reign. It is a reminder that our existence is woven from both fundamental law and fundamental chance, a cosmic lottery drawn in the first moment of time, with the grand prize being everything we see. Yet the blueprint for those galaxies required an invisible architect. While the quantum seeds provided the pattern, something else had to provide the gravitational muscle to pull that pattern into reality, long before ordinary matter was ready to do the job. This is where the most mysterious substance in the cosmos enters the story, a ghost that has shaped everything from the very first instant. Dark matter is the universe's invisible scaffolding, and its dominance was established when the universe was younger than a second. Unlike the protons, neutrons, and electrons that make up our world, dark matter does not interact with light or the electromagnetic force at all. It is utterly transparent and, for all practical purposes, intangible. But it does possess mass, and therefore it feels and exerts gravity. This simple fact made it the primary actor in the cosmic construction project. Current theories suggest dark matter likely consists of as yet undiscovered fundamental particles that stopped interacting with normal matter extraordinarily early, perhaps even before the first protons formed during primordial nucleosynthesis. While normal matter was a frenetic participant in the early plasma, constantly buffeted by radiation pressure, dark matter was aloof. It slipped through the brilliant chaos unaffected, a silent spectator with immense gravitational influence. This difference was everything. After inflation stretched the quantum seeds into cosmic ripples, both dark matter and ordinary matter felt the slight gravitational tug of those over dense regions. But ordinary matter, the protons and electrons, was still tightly coupled to the intense sea of radiation. Imagine trying to build a sandcastle while a powerful hose is spraying the sand. Every time a clump of protons tried to gather under gravity, the pressure from the relentless photons would blow it apart. Dark matter faced no such obstacle. Since it ignores light, it could begin to pool quietly into the gravitational wells of those initial fluctuations immediately. Its mass started to accumulate, deepening those wells and creating a hidden gravitational landscape, a skeleton upon which the visible universe would later be draped. This head start was critical. By the time the universe became transparent at 380,000 years and ordinary matter was finally freed from radiation's grip, dark matter had already laid down a vast, intricate network of gravitational potential. The normal hydrogen and helium gas simply flowed into the pre-existing valleys carved by dark matter's unseen mass. Without this invisible framework, the clumping of matter would have been far slower and less efficient, potentially delaying or even preventing the formation of the first stars and galaxies. The universe might have remained a diffuse, dim haze. So what could this elusive substance be? Leading candidates point to particles born in that first fiery moment. One prominent class is called weakly interacting massive particles, or WIMP. As the name suggests, these hypothetical particles would interact only through gravity and the weak nuclear force, making them incredibly difficult to detect. They are a compelling candidate because their predicted properties and abundance could naturally arise from the high-energy conditions of the early universe. Another fascinating possibility is the action, an extremely lightweight particle originally proposed to solve a different puzzle in particle physics. Actions would behave more like a coherent wave flowing through space rather than discrete particles. Experiments around the world are hunting for both. Deep underground laboratories seek the rare recoil from a WIMP bumping into an atomic nucleus, while other instruments search for the subtle conversion of actions into microwave photons in strong magnetic fields. The nature of dark matter is not just an academic curiosity, it is a question about the foundational ingredients of reality. If dark matter had possessed even a tiny ability to interact with light, or if it had been born with different properties, the cosmic story would have unfolded on a completely different stage. Galaxies might have formed in different shapes at different times, or perhaps not at all. The fact that we live in a universe where dark matter outnumbers ordinary matter by a factor of 5 to 1 is a direct outcome of processes in that first second, a silent decree that most of the cosmos would be built from something we cannot see. This uniform glow from the cosmic dawn presented cosmologists with a profound and unsettling mystery. If you look at the cosmic microwave background in one direction, and then turn to look in the exact opposite direction, you are seeing light that has traveled for over 13 billion years from two regions of space that are now nearly 28 billion light-years apart. According to the classic Big Bang model without inflation, these two regions could never have been in contact. The universe was not old enough for light or any influence to have traveled between them to exchange information and equalize their conditions. It is as if two people were placed at opposite ends of an impossibly vast desert with no means of communication, and yet they both independently wrote down the exact same story, word for word. How could regions that were never causally connected possibly know to reach the exact same temperature to such a stunning degree of precision? This was the horizon problem, and it suggested a flaw in our understanding of the universe's earliest moments. The solution required a radical rethinking of that beginning. Cosmic inflation provided the elegant answer. Before inflation, the entire observable universe was once contained within a tiny, microscopic patch that was small enough to be causally connected. Every part of that patch had ample time to mix and smooth out, reaching a uniform temperature and density. Then inflation acted. That hyper-accelerated expansion took that tiny, homogeneous marble and stretched it to a size far larger than our entire observable universe today. What we see as opposite horizons of the cosmos were once cozy neighbors, thoroughly mixed before being flung apart. The desert, it turns out, was once a single, well-stirred drop of water stretched into a vast ocean. This is why the afterglow looks the same in every direction. The regions were in intimate contact long before inflation pushed them beyond each other's light horizons. This resolution is a cornerstone of modern cosmology, demonstrating how an event in the first fraction of a second imprinted itself on the entire large-scale structure of reality. But solving the horizon problem was just the beginning. Inflation's incredible stretching also provided the key to another, equally fundamental puzzle about the shape of space itself. That profound uniformity also points to a deeper mystery about the very shape of reality. Observations tell us the large-scale geometry of the cosmos is flat, not in the sense of being two-dimensional, but in the way that parallel lines never meet or diverge. Think of it like the surface of a perfectly calm lake stretching to infinity. This geometric flatness is not just a curious fact, it is a condition of such extreme precision that it borders on the miraculous, and it presents the flatness problem. To understand the problem, picture the possible fates of the universe as three distinct geometric shapes. A closed universe would be like the surface of a sphere, where parallel lines eventually converge. An open universe would resemble a saddle shape, where lines perpetually diverge. A flat universe sits perfectly balanced between these two, a razor's edge where lines remain parallel forever. The fate of each geometry is tied to density. In a closed universe, there is enough matter and energy to eventually halt expansion and cause a collapse. In an open universe, there is too little, leading to eternal, thinning expansion. A flat universe has the precise critical density to balance expansion against gravitational pull, like a ball perfectly tossed to escape a planet's gravity without flying away forever. Here is the staggering part. For the universe to be as flat as we measure it to be today, 13.8 billion years into its expansion, its density in those first moments had to be fine-tuned to an almost impossible degree. At just 1 second old, the density of the cosmos needed to be within 1 part in 10 to the power of 60 of the critical density. That is a 1 with 60 zeros after it. To grasp that precision, imagine trying to balance a pencil on its tip, not for a second, but for the entire age of the universe. The slightest breath of air, the tiniest imperfection, would topple it instantly. The early universe faced a similar instability. Any small deviation from perfect flatness would have been magnified exponentially by expansion over billions of years. If it had started even slightly closed, it would have collapsed back on itself long before stars could form. If it had been slightly open, it would have expanded so rapidly that matter could never have clumped into galaxies. The fact that we are here in a stable, flat, structured cosmos seems to demand an explanation for that preposterously precise initial condition. How could such an exact balance have arisen by chance? Once again, cosmic inflation provides a powerful and elegant answer. The mechanism acts like a universal zoom lens. Imagine the surface of a giant balloon which is clearly curved. Now take a tiny patch of that balloon's surface, perhaps the size of a coin. To an ant standing on that small patch, the surface would appear perfectly flat. Inflation did exactly this to the entire observable universe. It took a minuscule, perhaps slightly curved region of the primordial cosmos and stretched it to a size far larger than everything we can see. From our perspective within that now vastly expanded patch, the geometry appears perfectly flat, simply because we are looking at such a small fraction of the original curvature. This dynamical process removed the need for miraculous 1 in 10 to the 60 fine-tuning. Instead, it made a flat universe a natural, almost inevitable prediction. Inflation took the question of why the universe is so flat and transformed it. We no longer need to ask why the initial conditions were set with impossible precision. Instead, we understand that our entire observable cosmos is just a small, smoothed-out piece of a much larger and possibly more varied whole. The flatness we measure is not a delicate starting condition, but a consequence of that explosive stretching in the first fraction of a second. This realization shifts our perspective from a universe finely tuned at birth to a universe whose local properties were shaped by a powerful, transformative event. The geometry we inhabit was not written in stone at the beginning. It was ironed into the fabric of space-time by inflation itself. But this perfectly smoothed and flattened universe should have been littered with cosmic fossils, relics of a broken symmetry that we simply do not see. Grand unified theories propose a breathtaking simplicity, suggesting that in the extreme heat of the very early universe, the strong nuclear force and the electroweak force were also one. As the cosmos cooled, this grand unified force would have broken apart, undergoing a dramatic phase transition. And just as cracks form in ice as water freezes, Such cosmic transitions can create topological defects, stable knots in the fabric of reality. The most famous of these predicted defects is the magnetic monopole. Unlike every magnet you have ever seen, which always has both a north and a south pole, a monopole would be a solitary, isolated pole, a fundamental particle that is either a pure source or a pure sink of magnetic field. These exotic objects are not just missing magnets, they are massive, stable, and should have been produced in staggering numbers during that grand unification epoch. According to standard calculations without inflation, the universe should be absolutely flooded with them today, with a density so high that they would be more common than atoms. Yet, despite decades of sensitive searches, from deep underground experiments to scans of moon rock and ancient minerals, not a single confirmed magnetic monopole has ever been found. Their profound absence is the monopole problem, a glaring contradiction between elegant theory and empty observation. How could the universe have lost something so fundamental? Once again, the answer lies in that explosive first instant. Cosmic inflation provides an elegant and necessary solution. If inflation occurred after the grand unified symmetry broke and monopoles formed, its incredible stretching would have diluted their density to virtually zero within our observable patch of the cosmos. It would have swept these primordial relics far beyond our cosmological horizon, effectively pushing them out of sight. The fact that we do not see monopoles is not a failure of the theories that predict them, but rather a powerful, indirect clue that inflation really happened. Their absence is a silent testament to the universe's violent, hyper-expansive infancy, a cleanup operation of cosmic proportions. This resolution of the monopole problem was one of the key motivations for Alan Guthr's original inflationary model, turning a theoretical headache into a predictive triumph. It makes us wonder what other relics from the first moment, these cosmic cracks in a frozen symmetry, might still be hiding in the vastness beyond what we can see. Could other, more subtle defects be woven into the fabric of spacetime itself, waiting to be discovered? To understand that first instant, we must move beyond the known laws. At the Planck scale, where general relativity and quantum mechanics clash, we require a theory of quantum gravity, a framework that can describe the fabric of reality when it was a foaming quantum sea. One of the most ambitious candidates for this ultimate theory is string theory, and it proposes a vision of reality more elegant and strange than any before it. The central idea is deceptively simple. The fundamental constituents of the universe are not zero-dimensional points, but incredibly tiny, vibrating loops or strands of energy, each smaller than a Planck length. Just as a single violin string can vibrate at different frequencies to produce distinct musical notes, these cosmic strings vibrate in different patterns or modes. One specific vibration might correspond to an electron, another to a quark, and yet another to the photon, the particle of light. In this symphony of strings, every particle and every force carrier in nature is unified, a different note played on the same elemental instrument. This elegant concept naturally incorporates gravity, with the graviton, the hypothetical particle mediating gravity, arising as another vibrational state of the string. But to make the mathematics of this vibrating symphony work, string theory demands more room than our familiar 3 dimensions of space and 1 of time. It requires extra dimensions of space, typically 6 or 7, curled up or compactified at scales so minute we could never perceive them directly. Imagine a long, thin garden hose viewed from a great distance. It appears as a simple one-dimensional line. Only upon closer inspection do you see its 2-dimensional surface, curled into a cylinder. The extra dimensions of string theory are thought to be similarly compactified, their geometry and shape determining the properties of our four-dimensional reality. The vibrational patterns of the strings, and thus the masses and charges of all particles, are set by the precise way these extra dimensions are folded. This leads to a staggering possibility known as the string landscape. Rather than predicting one unique universe, the theory suggests a vast multiverse of possible vacuum states, each with different compactified dimensions and therefore different physical laws and constants. Our universe, with its specific particle masses and force strengths, would be just one possibility among an almost inconceivable number, a single bubble in a cosmic froth of possibilities. Another profound idea within string theory is the brane world scenario. In this picture, our entire four-dimensional universe, with all its stars and galaxies, could be a membrane, or brane for short, floating within a higher dimensional space called the bulk. Other branes, hosting other universes with different physics, could exist parallel to our own in this bulk. This framework offers a dramatic reimagining of the Big Bang itself. What if our universe's violent beginning was not a singularity in empty space, but the result of a collision between two such branes floating in the higher dimensional void? The immense energy of that collision, reverberating across our brane, could have ignited the hot, dense state we call the Big Bang. This cyclic model suggests a cosmos without a true beginning, where brane collisions occur in an endless rhythm. Most radically, string theory allows us to speculate about a phase before geometry itself. In the very first instant, perhaps space and time as continuous, smooth concepts did not exist. They may have emerged from a more fundamental, pre-geometric state described by the interactions of strings and branes. In this view, the first moment was not an explosion in a void, but the crystallization of spacetime from a more primitive substrate, the first coherent notes rising from a formless vibrational chaos. This is the theoretical frontier where mathematics becomes our only guide into a realm beyond human intuition. Could the entire cosmos, in its first fleeting heartbeat, have been a symphony of strings vibrating the universe into existence? While still unproven and facing immense challenges, string theory represents our boldest attempt to write the score for that first, silent music. While string theory weaves extra dimensions into its symphony, another profound idea takes a radically different approach, building the cosmos from the fabric of spacetime itself. This is loop quantum gravity, a compelling alternative that reimagines the very first moment not as a bang but as a bounce. At its heart is a revolutionary proposal that space is not a smooth, continuous backdrop. Instead, it is woven from a network of incredibly tiny, discrete loops, a fabric of reality with a finite, granular structure. Picture the universe not as an infinitely divisible sheet of paper, but as a vast tapestry made from individual, interwoven threads. Each thread represents a quantum of area, and each intersection a quantum of volume. There is a smallest possible piece of space, a pixel of reality. This quantization resolves the violent clash between gravity and quantum mechanics at the Planck scale, replacing the formless singularity with a tangible quantum structure. In this framework, the story of our beginning transforms completely. The Big Bang was not an explosion from nothing, but a big bounce. Imagine the previous cosmic cycle, a universe like our own but contracting under its own gravity, growing hotter and denser as it collapsed. According to classical physics, this leads to the same impossible singularity. But loop quantum gravity introduces a repulsive force generated by the quantum nature of geometry itself. As density approaches the Planck scale, this force becomes overwhelmingly powerful, acting as a cosmic trampoline. The contraction halts, and the universe rebounds into a new phase of expansion. Our entire cosmic history, then, is one chapter in an endless book, a single expansion following a prior contraction. This elegant idea completely avoids the mathematical infinities of a singularity, offering a clear picture of a transition. There was no point of infinite density, only a maximum density where quantum geometry took command and turned the tide. This paints a vivid picture of the Planck epoch, not as a featureless fire, but as a seething quantum spacetime foam. In that dense, energetic state, the loops of the spin network would have been wildly fluctuating, a chaotic, probabilistic froth where conventional ideas of before and after could still hold meaning. The bounce represents a profound transformation, a moment of supreme density and heat, but not an absolute beginning. How would such a cyclical history reshape our understanding? It suggests our universe may be one episode in an eternal sequence, with no first cause and no final end. The laws of physics and the constants of nature could potentially be reborn with each cycle, or they might be transmuted through the bounce, leading to a cosmos similar to, but not identical with, the one that came before. This vision offers a different kind of answer to the haunting question of what came before. There was simply another phase of the cosmos, another universe living out its story on the other side of the bounce. While evidence for this model remains a subject of intense research, it demonstrates the incredible creativity of modern cosmology, using the quantum nature of spacetime to write a new origin story where the first moment is not an end, but a turning of the page. The bounce of one universe could be just a single heartbeat in an infinite cosmic body. The concept of a multiverse stretches this idea to its ultimate limit, proposing that our entire cosmic history is not unique but one of countless possibilities. This is the hypothesis of eternal inflation, a breathtaking extension of the inflationary model we discussed earlier. Recall that inflation was driven by a field perched in a high-energy state, which then rolled down a slope to a lower energy state, releasing its energy to reheat our universe. But what if that roll down was not uniform? Imagine a vast, bubbling pot of water just beginning to boil. In most of the pot, the water remains in a metastable state, superheated and ready to erupt. But here and there, bubbles of stable steam spontaneously form and expand. In eternal inflation, the fabric of spacetime is that superheated pot. Inflation, the rapid expansion, is the default, eternal state of a primordial false vacuum. But in random, rare locations, quantum fluctuations cause the inflattened field to tunnel or roll into a lower energy state. Each of these events nucleates a bubble universe. Within that bubble, inflation ends, and the energy released creates a hot Big Bang, setting off the chain of events that leads to stars, galaxies, and life. Our entire cosmos is one such bubble, a stable pocket in an eternally inflating sea. Crucially, because the tunneling events are random, the properties of each bubble can be wildly different. The way the fields settle, the number of dimensions that remain unfurled, the strengths of the fundamental forces, even the value of constants like the speed of light or the mass of the electron, could all be different in each separate universe. This forms what string theorists call the landscape, a vast, perhaps infinite, array of possible universes with every conceivable set of physical laws. This idea provides a dramatic answer to the haunting question of fine-tuning. Why does our universe have constants seemingly perfectly calibrated to allow for atoms, stars, and life? If there are an infinite number of universes, then every possible combination of constants exists somewhere. We, by necessity, find ourselves in one of the rare bubbles where the numbers allow for our existence. It is not that the universe was designed for life, but that life can only arise in a universe capable of producing it. This is the anthropic principle in a multiverse context. Philosophically, this reshapes our place in reality. Our universe is not the grand, singular stage of existence, but a single room in an endless cosmic mansion, most of which is utterly alien and inaccessible to us. Scientifically, it presents a profound challenge. If other universes are causally disconnected from ours, forever beyond the reach of any signal or observation, can the multiverse hypothesis ever be truly tested? Some scientists argue it moves beyond science into the realm of metaphysics. Yet, proponents search for potential signatures. Could our bubble have collided with another in the distant past, leaving a strange imprint on the cosmic microwave background? Could the specific pattern of quantum seeds we see hint at our bubble's nucleation? For now, these are open questions. In this view, the first moment of our universe was not the beginning of everything, but the nucleation of our local bubble from an eternal, inflating false vacuum. The singularity gives way to a quantum fluctuation in an endless, frothing ocean of potential. Are we living in a single universe or one of countless others? The answer stretches the concept of reality to its breaking point, suggesting that all we see and know is just one possible verse in an infinite, eternal poem. This silent, eternal multiverse leads us to a paradox at the very edge of physics. Black holes, those cosmic vacuums, present a famous conundrum known as the information paradox. According to quantum mechanics, information about the state of a physical system can never be truly lost. But a black hole, according to classical general relativity, evaporates over time through Hawking radiation, seemingly erasing all information about what fell into it. This creates a fundamental conflict between our two most successful theories of reality. Yet this paradox might not be confined to the dark corners of space. Could the origin of the universe itself present the ultimate information paradox? If our cosmos began from a singularity, a point of infinite density where all known laws break down, what happened to the information about whatever came before? Did the Big Bang act as a cosmic reset button, permanently erasing or scrambling the quantum information of a prior state? This question forces us to confront whether the universe, in its fiery birth, obeyed the same quantum rules that govern everything within it. The idea that information must be preserved is a cornerstone of quantum theory, a principle as fundamental as the conservation of energy. If it was violated at the beginning, it challenges our entire understanding of causality and reality. To find answers, we must look to one of the most radical ideas in modern physics, the holographic principle. This concept suggests that all the information contained within a volume of space can be fully described by the information encoded on its boundary surface. It is as if the three-dimensional world we experience is a projection, like a hologram, from a two-dimensional surface of information. For a black hole, this principle suggests the information of everything that ever fell in is not lost inside, but is smeared across its event horizon, the point of no return. Applied to the entire cosmos, this becomes a staggering proposition. The information describing every galaxy, every star, and every particle in our universe might be encoded on the cosmic horizon, the spherical boundary of our observable universe. In this view, the Big Bang singularity is not a wall but a transformation. The quantum information of whatever preceded our universe, perhaps a prior cosmic cycle or a quantum fluctuation in a multiverse, was not destroyed. Instead, it was translated, projected onto the expanding boundary of the new spacetime as it crystallized. The first moment was not an erasure, but an encoding. This directly connects the deepest puzzles in quantum gravity to the origin of everything. Understanding how information is preserved or transformed in the birth of spacetime could be the master key that unlocks a unified theory. It suggests that the universe's first instant was not a lawless chaos. but a process governed by a deeper, informational logic we are only beginning to decipher. How is the story of creation written not in stone, but in bits of quantum data on the skin of the cosmos? The answer lies in the mysterious link between the infinitesimal quantum world and the vast cosmic horizon, a connection forged in that first, fleeting heartbeat of existence. These silent messengers from the first second are still with us, a whisper from the moment matter itself was born. Among the most elusive inhabitants of the early universe were neutrinos, particles so ghostly they pass through entire planets as if they were empty space. In the seething plasma of the first second, they were produced in staggering numbers, a product of the intense interactions between radiation and matter. But their nature is one of profound detachment. As the universe expanded and cooled, neutrinos were the first to go their own way, ceasing to interact with the rest of the cosmic soup when the cosmos was barely a single second old. From that moment on, they have streamed freely through the expanding void, a permanent, silent population. This created a cosmic neutrino background, a sea of these particles that is even more ancient than the cosmic microwave background of light. While the light we see was trapped until atoms formed hundreds of thousands of years later, the neutrinos have been traveling unimpeded for the entire age of the universe. If we could sense them, they would be everywhere, a faint, cold relic with a present-day temperature of just about 1.95 Kelvin, even colder than the microwave afterglow. Each cubic centimeter of space around you is thought to contain over 300 of these primordial neutrinos, a ghostly fossil density that outnumbers atoms by over 1 billion to 1. Yet their ghostly nature makes them nearly impossible to catch. Detecting these specific, ancient neutrinos directly is one of the greatest experimental challenges in all of physics. They possess so little energy now that they slip through the most sensitive detectors ever built without a trace, but we are not completely blind to their influence. These particles, while intangible, have mass, and that mass exerts a gravitational pull. Their collective presence affected how the universe expanded in its youth and subtly shaped the patterns we see in the cosmic microwave background and the large-scale distribution of galaxies. They also played a crucial, subtle role during primordial nucleosynthesis. In those first 3 minutes, as protons and neutrons fused to form the first atomic nuclei, the presence of this vast sea of neutrinos influenced the nuclear reaction rates, helping to set the precise abundances of hydrogen and helium that we observe today. These faint whispers carry untapped information about conditions we can never directly observe, a snapshot of the universe at an age of 1 second, a time before light could travel freely. What could a dedicated neutrino telescope capable of capturing these ancient ghosts reveal? It would be a direct window into the universe's fiery infancy, offering a pristine view of a moment when the cosmos was a dense, opaque plasma, a perspective completely different from the picture painted by light. Unlocking their secrets would allow us to peer past the microwave background, deeper into the first heartbeat of existence than we have ever looked before. These ghostly messengers carry a hidden truth about the very rulebook of reality. The numbers that govern our universe, the fundamental constants, are not arbitrary. The speed of light, the strength of gravity, the mass of an electron, the force that binds atomic nuclei, each is a precise, dimensionless number. Their values were not written in stone at the beginning of time, but were almost certainly decided during the chaotic transitions of that first second, as symmetries shattered and fields froze into their current states. Think of these constants as the dials on a cosmic control panel. If even one were turned just a fraction, the universe would be unrecognizable. A slightly stronger gravitational constant, and stars would burn their fuel in a furious flash, collapsing into black holes before planets could form. A weaker, strong nuclear force, and protons and neutrons would never bind, leaving the cosmos a thin soup of hydrogen with no heavier elements. A different value for the fine structure constant, which governs electromagnetism, and the delicate bonds between atoms would fail, preventing chemistry itself. The precision required is staggering. It is as if someone dialed in a combination lock with 100 digits and got it right on the first try, creating a universe capable of building stars, planets, and conscious observers. This is the profound puzzle of fine-tuning. Why does our universe have a set of physical laws so exquisitely calibrated for complexity? One compelling line of reasoning is known as the anthropic principle. In its simplest form, it states that we observe the universe to be the way it is because if it were any different, we would not be here to observe it. We are not a lucky accident in a random cosmos, but a necessary outcome of its specific parameters. Our existence acts as a filter, selecting for the rare universes where life is possible. This idea finds a natural home in the concept of a multiverse. If eternal inflation or string theory's landscape is real, generating a vast or infinite array of bubble universes, each with randomly different constants, then it is no surprise we find ourselves in one of the rare, life-permitting bubbles. In this view, the fine-tuning is not evidence of design, but of selection bias. We are simply living in the neighborhood that allows for neighbors. Yet other theories propose the constants may not be eternal. Perhaps in the extreme energy of the first instance, they were not fixed but evolved, settling into their current values as the universe cooled, like a metal taking on a specific shape as it hardens. Some models even suggest subtle variations could still exist across vast cosmic distances, a remnant of that early plasticity. Regardless of the explanation, the moment of locking was decisive. When the Higgs field acquired its value, when the forces separated, when extra dimensions curled up, the dials were set. That first second wrote the operating manual for everything to come. It determined how stars would shine, how atoms would bond, and how time would flow. The constants are the silent, unchanging language in which the story of the cosmos is written. Their precise values allowed a formless fire to condense into a structured, evolving, and ultimately living universe. The deepest mystery is not just that the numbers are right, but that they had to be right at the very beginning, in a flash of existence too brief to measure for any story to be told at all. That silent rulebook of constants presents our greatest observational challenge. We can never look directly at the universe in its first second, for the simple reason that light itself was imprisoned. The cosmos was an opaque, glowing plasma, a brilliant fog that no traditional telescope could ever pierce. To understand that hidden era, we must become cosmic detectives, reconstructing the crime scene from fragments of evidence left behind billions of years later. Our methods are ingenious and indirect, each one a forensic tool for a different aspect of the primordial fire. The first approach is to turn back time in a laboratory. Giant particle accelerators like the Large Hadron Collider smash protons together at velocities approaching the speed of light. In the heart of those collisions, for a fleeting instant, we recreate the seething energies and densities that existed when the universe was less than a trillionth of a second old. By studying the Quark-Gluon Plasma and the particles that spray out, we test our theories of how matter behaves under conditions that have not existed naturally since the beginning. It is a tiny, human-made glimpse into that first cosmic forge. Another promising clue is etched into the oldest light we can see. Scientists meticulously study the polarization, or the orientation, of the cosmic microwave background photons. Within that subtle pattern, they search for a specific swirling signature known as B modes. This distinctive curl could be the imprint of primordial gravitational waves, ripples in space-time itself generated during the violent expansion of cosmic inflation. Finding this signal would be like discovering the fossilized footprints of the universe's first explosive growth spurt, direct evidence from a time before even particles existed. Then there is the hunt for the universe's oldest ghosts. As we discussed, a cosmic neutrino background from the first second should permeate all of space. Detecting these specific, ultra-low energy neutrinos is a monumental technical challenge, but success would give us a pristine snapshot of the cosmos at an age of 1 second, a messenger from a time even older than the microwave background. Finally, we look at the large-scale structure of the universe itself. The way galaxies are clustered into a vast cosmic web today holds a memory of the initial quantum seeds. By mapping millions of galaxies with projects like the Sloan Digital Sky Survey, astronomers can search for subtle statistical patterns that might reveal details about early phase transitions or exotic particles from the first instance. It is like deducing the recipe of a cake by carefully studying the pattern of its crumbs. Each of these methods is a piece of the puzzle, and none alone can give the full picture. This quest demands a profound collaboration across disciplines, uniting particle physicists who understand the smallest scales with astrophysicists who map the largest structures, all guided by the theories of cosmologists. The challenges are immense, pushing the limits of engineering, computing, and pure imagination. What new technology might finally allow us to peer into the Planck epoch itself? Perhaps quantum sensors of unimaginable sensitivity, or space-based observatories that can measure the cosmic microwave background with even finer detail. The drive to witness our own origin story is fueling innovation at the very edge of science, reminding us that the first second, though forever hidden from direct view, is not beyond the reach of human curiosity. The search for our origin ultimately leads to a question that science alone cannot answer. If time itself had a definitive beginning in that first second, what does that mean for existence? This is not merely a scientific puzzle, but a philosophical and perhaps even a spiritual frontier, forcing us to confront the very nature of reality and causality. Our everyday logic is built on a simple chain, cause and effect. Every event we see is the result of something that came before it. But if the Big Bang represents the absolute beginning of time, then the chain hits a wall. What could have caused the first cause when there was no before for a cause to exist in? This paradox stretches human reason to its limit, inviting profound contemplation from every corner of human thought. For many theological traditions, a temporal beginning aligns powerfully with the concept of creation from nothing, a moment where a transcendent reality beyond space and time brought the cosmos into being. In this view, the singularity is not a physical object to be explained, but a boundary marking the transition from non-being to being, a moment of divine fiat where the laws of physics themselves were spoken into existence. It is seen as the ultimate evidence of a foundational mind or will, answering the question of why there is something rather than nothing with a purposeful act. Secular and naturalistic philosophies, however, seek explanations that remain entirely within the fabric of physical law, even if those laws operate in realms beyond our current understanding. They point to ideas emerging from quantum cosmology, where the universe could have spontaneously arisen from a quantum fluctuation in a metastable vacuum, a state of pregnant nothingness seething with potential. In this framework, nothing is not an empty void, but a rich, dynamic arena governed by quantum principles. The universe, then, is its own cause, a self-contained entity that popped into existence as a natural consequence of deeper, eternal mathematical truths. This blurs the line between something and nothing in a way that challenges our classical intuition. The quantum vacuum from which such a fluctuation might arise is not nothing in a philosophical sense. It is a something with specific properties and potentials. So the debate often circles back to definitions. What do we truly mean by nothing? Is it the absence of all things, including physical laws and potential? Or is it a state of perfect symmetry and zero net energy which can, through its own inherent instability, give birth to a cosmos? The first second forces this confrontation. It places us at the precipice where our language and logic, built in a world of continuous time and clear causality, falter. We are left contemplating whether the universe requires an external explanation, a creator, or if it is a self-explanatory, necessary entity, a brute fact of existence that simply is. Perhaps the most humbling realization is that our minds, evolved to navigate a world of middle-sized objects and linear time, may be fundamentally ill-equipped to grasp the true nature of ultimate origins. We are like ants trying to comprehend the architecture of a skyscraper, using tools and concepts that work perfectly well on the forest floor but fail at the scale of the human-made structure. The mystery of the first second thus becomes more than a scientific target. It is a mirror reflecting the limits of our own understanding. It invites a kind of intellectual humility, a recognition that some truths about existence may forever reside just beyond the reach of empirical proof, in the realm of awe, wonder, and perpetual inquiry. Yet to truly witness that first second, we must build our own universe inside a machine. Since we cannot rerun the Big Bang in a lab, scientists construct breathtakingly complex digital worlds, using the most powerful supercomputers on Earth to simulate the dawn of everything. These are not simple animations, but living mathematical models where every particle, every force, and every law of physics is encoded into billions of lines of equations. The simulations begin with the initial conditions we believe existed in that primordial fire, the smoothness from inflation and the faint quantum seeds. Then they let the clock run forward, allowing the immutable laws of gravity, nuclear physics, and fluid dynamics to play out over cosmic time. To recreate the Quark-Gluon Plasma of the first microsecond, they use equations from quantum chromodynamics. To model the explosive growth of inflation, they solve the complex fields of general relativity. To follow the forging of the first hydrogen and helium nuclei, they calculate the precise rates of nuclear fusion and decay. Each of these epochs presents a monumental computational challenge, requiring processors to perform quintillions of calculations per second. One of the most ambitious of these projects is called Illustris, the next generation. This simulation does not just model a patch of empty space, it creates a virtual cosmos, a cube of digital reality over 1 billion light-years on a side. Within it, the code tracks the gravitational pull of dark matter, the hydrodynamics of collapsing gas clouds, the explosive feedback from supernova, and the formation of black holes. Starting from a near-uniform state just after the cosmic microwave background was released, it fast-forwards through 13.8 billion years of evolution. The result is staggeringly beautiful, a swirling digital tapestry that emerges from the equations, showing galaxies with distinct spiral arms, clusters, and vast voids that mirror our own observed universe with uncanny accuracy. These virtual time machines serve a crucial purpose. They are testing grounds for our theories. Scientists can tweak the initial parameters. What if dark matter was slightly warmer or colder? What if the primordial density fluctuations were a bit different? And then run the simulation to see what kind of cosmos emerges. By comparing the final digital universe with the real one we observe through telescopes, they can rule out some ideas and validate others. It is a process of cosmic deduction, using silicon and code to explore possibilities that are forever locked in our past. But how accurate can a simulation of all reality truly be? They are, by necessity, approximations limited by our current knowledge and the finite power of even our greatest computers. Yet they are our best digital proxies, allowing us to perform experiments on the universe itself, to watch in fast motion the consequences of decisions made in that first, fleeting heartbeat of time. The digital universes we create are only as good as the data we feed them, and a new wave of observation is about to flood our models with unprecedented detail. The quest to understand the first second is accelerating, driven by a global array of missions and experiments designed to capture the faintest echoes of creation. Each new instrument acts as a sharper lens, allowing us to peer further back in time, closer to that initial flash, by examining its enduring consequences. Leading this charge is the James Webb Space Telescope, an observatory that is fundamentally rewriting the book on cosmic dawn. By gazing at the most distant, ancient galaxies, Webb is not just studying stars, it is looking at the end product of a chain reaction that began in the first second. The size, shape, and chemistry of these earliest galactic structures carry subtle imprints of the initial density seeds and the nature of the dark matter that sculpted them. By mapping how galaxies assembled in the universe's first few 100 million years, we can work backwards, testing our theories of how those primordial quantum ripples grew into the cosmic web we see today. It is like finding the first paragraphs of a lost epic, giving us clues about the opening sentence. While Webb looks at the first structures, other ambitious projects aim to see the moment of creation itself, or at least its direct signature. On the high, dry plateaus of Chile and Antarctica, a new generation of ground-based observatories is coming online. The Simons Observatory and the planned CMBS-4 project are ultra-sensitive arrays of telescopes designed for one primary goal: to scour the cosmic microwave background for a specific, elusive pattern known as B-mode polarization. This faint, swirling signature in the oldest light is the predicted fingerprint of primordial gravitational waves, ripples in space-time generated during the violent expansion of cosmic inflation. Finding this signal would be the smoking gun for inflation, offering direct evidence from a time when the universe was a fraction of a second old. It would be the closest we could ever come to observing that explosive growth spurt, a snapshot of the universe's first and most dramatic transformation. The search also continues deep underground and within colossal rings of metal. Next-generation particle colliders, even more powerful than the Large Hadron Collider, are on the drawing board. Their goal is to reach ever higher energies, recreating conditions that existed closer and closer to the Planck epoch, potentially producing particles or revealing phenomena we have only theorized about. In tandem, incredibly sensitive dark matter detectors, shielded from cosmic rays in mines and tunnels, continue their patient watch for a signal from the universe's dominant but invisible substance. Detecting a dark matter particle would not only solve a major modern mystery, but would open a direct window into the physics of the very early universe, a time when these particles first decoupled from the primordial fire. These endeavors represent a monumental, collaborative effort across continents and scientific disciplines, a shared human project to peel back the layers of cosmic history, one after another. What breakthrough awaits us in the next decade? It could be the detection of a primordial gravitational wave pattern, the identification of a dark matter particle, or an observation from Webb so unexpected it forces us to rethink our entire timeline. Any one of these could revolutionize our origin story, providing the missing piece that finally allows us to construct a complete and coherent narrative from the first instant to the present day. We stand on the threshold of a new era of discovery, where the questions posed by that first, unimaginable second may finally find their answers not in theory alone, but in the clear, unambiguous language of data. The most persistent image of our origin is also profoundly wrong. We often visualize the Big Bang as a titanic explosion, a cosmic bomb detonating in a dark, empty void, flinging galaxies outward like shrapnel from a single point. This compelling picture is everywhere from textbooks to documentaries, but it fundamentally misrepresents what happened. The Big Bang was not an explosion in space. It was the explosive expansion of space itself. This distinction is not just a technicality, it reshapes our entire understanding of reality. There was no pre-existing emptiness for the universe to expand into, because space, time, and matter all came into being together in that initial event. Think of it this way: an explosion has a center, a ground zero from which debris flies outward, but the expansion of the universe has no such center. Every single point in the cosmos, the space between the stars in a distant galaxy, the atoms in your hand, and the void between galaxy clusters, all of it was once packed into that same primordial hot density. As space expanded, it carried everything with it, like raisins baking in an infinitely rising loaf of bread. No raisin is the center, each one sees all the others moving away. This is why astronomers observe that galaxies are receding from us in every direction. The entire cosmic loaf is stretching. This also dismantles another common myth, the search for a location. We cannot point to a spot in the night sky and say, the Big Bang happened over there. It happened everywhere because everywhere was once right here in that state of extreme compression. The entire observable universe, all 93 billion light-years of it, was once contained in a volume smaller than a single atom. That means the space you occupy right now was once part of that unimaginable fire. You are not made from debris flung from a distant blast. You are made from the very fabric of that initial state, cooled and transformed over billions of years. This model also clarifies that the Big Bang does not inherently conflict with many theological perspectives on creation. The scientific narrative describes the how, the physical process that unfolded from an initial state. It remains silent on the why, or what, if anything, precipitated that state from a realm beyond physics. Many find the two frameworks address different kinds of questions, one of mechanism, the other of meaning and ultimate cause. So how did the explosion myth become so entrenched? It is a natural shortcut for our brains, which are wired to understand events within a pre-existing stage. We think in terms of before and after, here and there. The concept of space and time being created, of a beginning to beginnings, is extraordinarily difficult to visualize. Clear communication is our greatest tool for correction, replacing the flawed but familiar bomb with the more accurate, if stranger, image of stretching spacetime. Grasping this true nature is essential, for it dictates the geometry of the cosmos and frames every question we have about its ultimate fate. That cosmic story is not a distant legend, it is our family history written in atoms. The iron in your blood, the calcium in your bones, and the oxygen you breathe were not present in the first second, but their possibility was irrevocably set in motion then. The chain of causality that leads directly to you began with those quantum seeds stretched by inflation. Those microscopic ripples dictated where the first clouds of primordial hydrogen and helium would begin to collapse under the silent pull of dark matter. Within those clouds, gravity ignited the first stars, colossal furnaces where the universe performed its second act of alchemy. In their searing cores, the simple hydrogen and helium forged in the first 3 minutes were fused into heavier elements: carbon, oxygen, nitrogen, and iron. When those first giant stars ended their lives in spectacular supernova explosions, they scattered these newly forged elements across space like cosmic seeds. This enriched gas coalesced into new generations of stars, planets, and eventually the rocky world we call home. The carbon that forms the backbone of every molecule in your body was once stardust, created in a stellar forge that itself was born from a density fluctuation imprinted in the first fraction of a second. You are literally made from remnants of the universe's first raw materials, processed and recycled across billions of years. This is not a metaphor, it is a physical fact confirmed by spectroscopy, the study of starlight, which reveals the same elemental signatures in distant nebulae as in our own solar system. The universe did not simply happen around us, we are its blossoming complexity, a way for the cosmos to know itself. Every person you meet, every living thing you see, is a temporary assemblage of atoms with a lineage tracing back to the initial fire. This perspective transforms our place in the cosmos from accidental bystanders to active participants in an ancient, ongoing narrative. The laws that allowed galaxies to form are the same laws that allow your heart to beat and your mind to ponder these very ideas. So when you look up at the night sky, you are not looking out at a foreign expanse. You are looking back at your own extended heritage, a reflection in a mirror 13.8 billion years deep. How does this change our view? It replaces a feeling of smallness with a profound sense of connection. We are not insignificant because the universe is vast. We are remarkable because we are the universe, conscious and curious, examining the very processes that led to our existence. That fleeting first second was not just the birth of space and time. It was the first note in a symphony that would eventually include you. This profound connection between the cosmic and the personal is rooted in a timeless human impulse. Long before telescopes or particle colliders, our ancestors looked to the stars and told stories of creation. Every culture, from the Dreamtime narratives of Aboriginal Australians to the cosmic egg of Hindu scriptures, from the Genesis account to the emergent world of Norse mythology, crafted its own explanation for how everything began. These myths were not primitive science, they were frameworks of meaning, attempts to place human life within a grand, purposeful narrative. They answered the fundamental questions of why we are here and what our place is in the grand scheme of things. Today, we continue that same essential quest, but our tools have evolved. We have exchanged oral tradition for mathematics and ritual for the rigorous, repeatable experiment. The scientific story of the first second is our modern creation myth, built not on revelation but on observation, evidence, and a relentless drive to test our ideas against reality. It is a narrative still being written, with each new discovery adding a sentence, a paragraph, sometimes a whole new chapter. What unites these ancient and modern pursuits is a shared sense of awe, a humbling wonder in the face of existence itself. Contemplating that a universe of such breathtaking scale and intricate beauty could emerge from a fleeting quantum tremor is an experience that transcends data. It is a feeling. It is the dizzying realization that the rules permitting planets and life were locked into place in a span of time too brief for any clock to measure. This awe is not a side effect of science, it is its engine. It is the quiet gasp that drove a curious mind like Albert Einstein to ponder the nature of space and time, and the same wonder that compels a team today to analyze the subtle patterns in the cosmic microwave background for a decade. It is the fuel for both the scientist at her desk and the child gazing up at a dark sky, filled with the same unanswerable question. Living in a universe with such a spectacular beginning changes our sense of scale. Our daily worries and triumphs, while deeply meaningful to us, unfold on a stage of almost incomprehensible grandeur. This perspective can be liberating. It invites us to see ourselves not as separate from the cosmos, but as an active, conscious expression of its underlying processes. We are the universe thinking about itself. The hydrogen formed in the first 3 minutes, the carbon forged in a long-dead star, the neural pathways sparked by curiosity. They are all part of one continuous 13.8 billion year-long event. This story does not diminish human significance, it redefines it. Our drive to understand, to connect the dots from the first instant to the present, is perhaps the most remarkable outcome of that initial cosmic evolution. So what does it all mean? Science offers a how, a magnificent and detailed mechanism. The why remains a territory for personal reflection, for philosophy, for art, and for the quiet moments of insight that come not from a textbook, but from simply being part of something so much larger than ourselves. The ultimate lesson of the first second may be that the quest for understanding is itself a beautiful and essential part of the cosmic story, a way for the universe to marvel at its own existence. But to truly grasp the alien nature of that moment, step away from the equations and into a hypothetical front-row seat. If you could somehow witness the universe's first second, your experience would defy every human sense and intuition. You would not be floating in darkness watching a distant fireball. You would be immersed in the fireball itself, a state of existence so extreme that the very concepts of sight, sound, and touch lose all meaning. There is no empty space around you, only a solid, seething ocean of pure energy. The temperature is not merely hot, it is a number beyond comprehension, so high that the idea of heat as a transfer of energy is meaningless because everything is at the same impossible intensity. In this bath of energy, no structures can hold. Molecules are an impossible dream. Atoms cannot exist, their electrons ripped away instantly. Even atomic nuclei, the protons and neutrons we consider fundamental, are melted into their constituent quarks and gluons, swimming freely in a formless, churning soup. Your vision, if such a thing were possible, would be a blinding, featureless glare from constant particle and antiparticle annihilations, a light so intense it has no color, only pure white energy. Yet you would feel no warmth because there is no cooler environment for heat to flow into. You would simply be the energy, a temporary pattern within it. The most profound sensation would be one you could not feel at all, the hyper-accelerated stretching of space itself. There is no wind rushing past because space is not moving through anything. It is the very fabric of reality that is expanding, carrying you and every point of energy along with it. You are not being pulled, you are being stretched, an expansion so rapid it happens everywhere at once. In this realm, time as a steady, ticking clock does not exist. The sequence of events is governed by energies and probabilities, not by seconds and minutes. The idea of before and after blurs in the quantum foam. Could any form of consciousness as we understand it exist here? It seems impossible. Consciousness requires stable structures, information processing, a separation between self and environment. In the primordial fire, there is no stable self, only a fleeting, interconnected fluctuation. This thought experiment is not just a flight of fancy. It is a tool to highlight why the first second remains a realm of theory and inference, not direct observation. It was a state of reality governed by laws that operate far outside our everyday experience, a place where the familiar rules of physics were being written in real time. To witness it would be to witness a reality before reality, as we know it had taken shape, a chaos of potential moments away from crystallizing into the cosmos we call home. Yet for all we have uncovered, the first second is still a realm of profound mystery. We have mapped the cosmic afterglow and recreated quark soup in colliders, but the deepest questions about our origin remain unanswered. Each one points directly back to the conditions of that fleeting epoch, as if the universe locked its ultimate secrets inside a time capsule from the moment of its birth. The most pressing is the search for a theory of quantum gravity. Albert Einstein's general relativity paints a beautiful picture of gravity as the curvature of spacetime, while quantum mechanics governs the probabilistic dance of particles. Both are spectacularly successful, yet they are fundamentally incompatible. In the extreme densities of the Planck epoch, where gravity and quantum effects were equally powerful, our current laws simply break down. We need a new framework, a set of rules that can describe a universe where spacetime itself is foamy and probabilistic. Without it, we cannot truly describe the moment of Genesis, or even say if there was a moment at all. Then there is the mystery of inflation itself. We have strong evidence that it happened, but we do not know what drove it. What was the inflaton field, and why did it have the precise properties needed to stretch the cosmos so perfectly? What caused it to roll down its energy slope and end? The trigger for this hyper-expansion is hidden from us, a cosmic starter pistol fired in a realm our telescopes cannot see. And what of the universe's invisible ingredients? Dark matter, whose gravitational pull sculpted the galaxies, is still an anonymous ghost. We feel its effects everywhere, but we have yet to identify its particle. Was it forged in the first second? Similarly, dark energy, the mysterious force accelerating the expansion of the universe today, presents an even deeper puzzle. Its nature seems to be tied to the vacuum of space itself, a cosmological constant whose tiny value is inexplicably fine-tuned. Did its value get set during an early phase transition? These two shadows dominate the cosmos, yet we do not know what they are. These questions inevitably lead us to the nature of time itself. Did time have a true beginning, or does it extend infinitely into the past in some form we cannot yet conceive? The classical Big Bang suggests a start, but theories like the Big Bounce or the Multiverse propose an eternal cycle. The answer determines whether the question what came before is meaningless or merely unanswerable from our vantage point. This opens the door to the most expansive possibility of all, the multiverse. Is our universe, with its specific laws and constants, just one bubble in an endless, frothing cosmic foam? If eternal inflation is correct, then our entire cosmic history is a local event within a much grander, perhaps infinite, meta-reality. This idea could explain the baffling fine-tuning we see, not as a miracle, but as a selection effect. We find ourselves in a bubble where life is possible simply because we could not exist in any other. Finally, all of this shapes the ultimate fate of everything. Will the universe expand forever into a cold, dark emptiness, a heat death where all energy is evenly distributed and no work can be done? Or could the expansion reverse, leading to a dramatic big crunch? The answer depends on the precise balance between dark energy, matter, and the geometry of space, parameters that were likely determined in that first fiery instant. Acknowledging these immense unknowns is not an admission of failure. It is a map of the frontier. Every great mystery listed here is a beacon, guiding the next generation of telescopes, colliders, and brilliant minds. The first second is not a solved puzzle. It is the master key that we are still learning how to turn. Which of these doors will we unlock first? The journey to understand our own beginning has only just started. The mysteries of the cosmos are not locked away in ivory towers. They belong to anyone with a spark of curiosity, and today, more than ever, you can join the quest to understand them. If the story of that first second has ignited a desire to learn more, you stand at the beginning of your own journey of discovery. the path from wonder to understanding is paved with incredible resources, many of them just a click away. A wonderful place to start is with the voices of scientists who are also master storytellers. Books by authors like Brian Greene, with his elegant explorations of string theory and the fabric of the cosmos, or Sean Carroll, who unpacks the deepest questions of time and reality, translate complex ideas into compelling narratives. For a gripping look at how it might all end, Katie Mack's work on the ultimate fate of the universe is both brilliant and accessible. These writers act as personal guides, turning the abstract into the tangible. To follow the discoveries as they happen, connect directly with the engines of exploration. Institutions like NASA, the European Space Agency, and CERN maintain vibrant social media channels and websites, offering breathtaking images, breaking news about distant galaxies or new particles, and behind-the-scenes glimpses of the instruments rewriting our textbooks. It is like having a front-row seat to history, watching the scientific process unfold in real time. For a more structured dive, the world of online learning opens doors that were once closed. Platforms like Coursera and edX host courses from leading universities on topics ranging from the Big Bang to exoplanets, allowing you to learn at your own pace. And for a visual feast that stirs the soul, timeless documentary series like Cosmos, in both its Carl Sagan and Neil deGrasse Tyson iterations, weave science and history into a grand, inspirational tapestry. Do not forget the power of a hands-on experience. Your local planetarium or science museum is a portal to the stars, offering shows that project the universe onto a dome above you and exhibits that make cosmic scales physically real. Standing beneath a simulated night sky or touching a model of a Martian rover makes the vastness personal. Engaging with these resources does more than fill your mind with facts. It transforms you from a spectator into a participant, a citizen of the cosmos. The story of our universe is still being written, with new chapters added every day by telescopes peering deeper and colliders probing finer. By following along, you become part of that ongoing narrative, sharing in the collective awe of discovery. How can you begin? Start with a single book, a single documentary, or a single visit to a museum website. Let that one step lead to the next. The greatest journey, after all, begins with a moment of curiosity, and the entire universe is waiting to be explored. This shared journey of discovery is not the work of a single nation, but a testament to our collective curiosity. The quest to understand the universe's origins is a fundamentally human endeavor, one that transcends political borders and cultural differences, uniting minds across the globe in a common purpose. Look at the monumental achievements of our time. The first image of a black hole's shadow was captured not by a single telescope, but by the Event Horizon Telescope, a planet-scale array linking observatories from the high deserts of Chile to the peaks of Hawaii and the mountains of Spain. It is a collaboration of over 300 researchers from more than 80 institutions across the world, a synchronized global effort to see the unseeable. Similarly, the Large Hadron Collider at CERN is a cathedral of cooperation, built and operated by a consortium of 23 member states, with thousands of scientists from over 100 countries analyzing its data. These are not just scientific instruments, they are symbols of what humanity can achieve when we pool our resources, intellect, and ambition toward a shared goal. This international framework is essential, as the scale of the questions now demands facilities and budgets that no single country could reasonably shoulder alone. It transforms competition into collaboration, where a breakthrough in Geneva is celebrated in Tokyo, and data from a telescope in Antarctica is analyzed by a team in California. This pursuit, however, requires immense investment, which naturally leads to a vital conversation about priorities. In a world facing urgent challenges, why dedicate billions to peer into the first second of time or collide particles in a tunnel underground? The answer is multifaceted and profound. The most immediate benefits often come in the form of spin-off technologies. The quest to create the World Wide Web at CERN to share particle physics data revolutionized global communication. Advances in medical imaging, from PET scans to cancer therapy, have roots in particle detection technology. The exquisite precision required to build gravitational wave observatories like LIGO drives innovations in laser and measurement science. These are tangible returns on a fundamental investment, but the value runs deeper than applications. Investing in fundamental science is an investment in our collective future. It is a commitment to pushing the boundaries of human knowledge, to answering the most profound questions of our existence. This pursuit cultivates a unique mindset, one of rigorous inquiry, creative problem-solving, and resilience in the face of the unknown. It trains generations of thinkers and engineers whose skills ripple through every sector of society. Most importantly, it fosters a perspective that is desperately needed. By revealing our common cosmic origin, this science underscores a powerful truth. Every human being, every nation, every culture is made from the same stardust, forged in the same ancient stars, and shaped by the same laws of physics written in the universe's first heartbeat. It frames our planet not as a collection of separate territories, but as a pale blue dot, a fragile and shared oasis in the vast cosmic dark. This knowledge does not solve geopolitical conflicts, but it offers a foundational narrative of unity that can inspire cooperation on other global challenges, from climate science to public health. How does funding a telescope or a collider shape our future? It shapes it by nurturing a sense of shared wonder, by driving technological innovation that improves lives, and by reminding us that in the grand story of the cosmos, we are all crew members on the same small ship, sailing together through an ocean of mystery. The pursuit of our origin is ultimately a celebration of what connects us, a project that belongs to all of humanity. The entire cosmic story, from unity to structure, unfolded in less than a single heartbeat. To grasp that impossible speed, let us lay out the sequence, a timeline of transformation more dramatic than any in the billions of years that followed. It begins at time zero in the Planck epoch, a span so brief it is measured from the very first instant to 10 to the negative 43 seconds. Here, the four fundamental forces were one, and space and time were a quantum foam, a realm where our current laws of physics simply break down. Then, around 10 to the negative 36 seconds, a monumental shift likely occurred. This is the era of grand unification and cosmic inflation, where a single, unified force may have split, and the universe underwent a hyper-accelerated expansion, stretching a quantum patch into our entire observable cosmos and planting the seeds for all future galaxies. As the cosmos continued to cool, another symmetry shattered at around 10 to the negative 12 seconds. The electroweak force split into the weak nuclear force and electromagnetism, and through the Higgs mechanism, particles like the W and Z bosons gained mass, giving substance to the universe. By 1/1,000,000th of a second, the temperature had fallen enough for a new state of matter to emerge, the Quark-Gluon Plasma, a seething, liberated soup of the most fundamental building blocks. This could not last. As cooling continued, quarks and gluons condensed in a process called hadronization, snapping together to form the first stable protons and neutrons, the bedrock of atomic nuclei. Then, at the 1-second mark, a great decoupling happened. The universe became transparent to ghostly neutrinos, which streamed away freely, creating a cosmic neutrino background that still permeates space today. Immediately after, the stage was set for the first nuclear fusion. Primordial nucleosynthesis began, forging the first atomic nuclei, hydrogen and helium, from that primordial proton-neutron soup in just 3 minutes. This entire cascade, from a formless unity to a universe stocked with the ingredients for stars, happened faster than you can snap your fingers. Each event was a domino, critically dependent on the one before it. The smoothness from inflation allowed forces to separate cleanly. The masses given to particles dictated how they would interact in the quark soup. The surplus of matter over antimatter meant there were survivors to form protons. The properties of neutrinos influenced the nuclear reactions that set the cosmic abundance of elements. This chain of causality, link by precise link, connects the unknowable quantum realm of the first instant to the tangible, structured cosmos we inhabit. How do we hold such an immense narrative? Not by memorizing the numbers, but by feeling the elegant, inevitable logic of it. Every galaxy, every planet, every life form is the product of that first second's flawless, breathtaking choreography. The story of that first second is a legacy of both majesty and enduring mystery. We have traced the cosmic chain from a formless quantum fire to the first stable particles, from a runaway expansion that smoothed the cosmos to the delicate asymmetry that allowed matter to survive. Every link in that chain, forged in less time than a human heartbeat, was essential. Without the precise breaking of symmetries, the specific surplus of matter, or the exact pattern of quantum seeds, our universe would be a dark, empty, or utterly alien place. There would be no galaxies, no stars, no Earth, and no one to wonder about it all. This realization is humbling and exhilarating. It means the air in your lungs and the light in your eyes are direct descendants of that primordial forge. You are not just in the universe, you are a vital, conscious part of its ongoing story. The astronomer Carl Sagan captured this beautifully when he observed that we are a way for the cosmos to know itself. Our curiosity is not separate from the universe, it is the universe becoming aware of its own origins and structure. This quest for understanding, from the first stories told around ancient fires to the equations written in modern labs, is a profound expression of that cosmic self-awareness. The mystery of the first second is far from solved. It continues to beckon, challenging the brightest minds and inspiring the most ambitious experiments. What new instrument, what unforeseen discovery will finally let us peer behind the veil of the Planck epoch? The answers wait in the data of next-generation telescopes, in the depths of underground detectors, and in the collective imagination of a species born from stardust, determined to read its own origin story. This journey does not end here. If this story of cosmic dawn resonated with you, share your thoughts and questions in the comments below. Your perspective adds to this grand conversation. And if you want to join us as we continue to explore the deepest mysteries of space, time, and reality, subscribe to the channel. Together, we will keep looking back so we can understand where we came from and perhaps glimpse where we are going. Thank you for exploring the first second of everything.